Hello, good morning. There is a famous quote in military planning. It's a favorite quote of mine. And it goes like, amateurs talk tactics, professionals talk logistics. You could probably guess that a logistician told me that one. I have some crazy hard logistics and supply chain problems that I would really love your help to figure out, okay? And I'm gonna explain them to you, but I hope that as I do so, you come to appreciate them for the very interesting, very hard problems, the DARPA hard problems that I think they are. So as a bit of background, I'm Julian McMorrow. I've been a program manager for about 5 months. Before that, I was a CETA in MTO for about 5 years. Before that, I supported the United States Marine Corps working on their expeditionary logistics work. The Marines being Marines, they like to work in a way that they describe as expeditionary, and that effectively what that means is they will be forward deployed, they will be self-sufficient, and they're gonna take everything with them that they need, right? And they do this because they plan to operate in places where they don't want to rely on a conventional supply chain, okay? So in support of this, they've been working on what they call expeditionary fabrication, and for them, that means 3D printing of repair parts where they need them and when they need them, right? They do this because they don't want to wait months to get a part from across the ocean. So this is a hard problem. They've been working on this for years. DARPA is working on this. All the services are working on this, but really this is just talking about mechanical parts, right? Static parts. Myself, coming from this background and then coming to MTO, I wanted to think about what it would mean to do expeditionary fabrication of microelectronics. And in particular, how would we supply our warfighters without a supply chain? Okay, so what do we know about upset supply chains for microelectronics? We know that for years, sanctions on the Russians have denied them the critical microelectronics that they need to wage war. But we also know that they've been able to circumvent those sanctions and those restrictions by going out and purchasing dishwashers and refrigerators and taking the chips out of them and putting them into their weapons, right? So here's a proof of concept, an existence proof that you can take parts with commercial utility and turn them into weapons with military utility. A little closer to home, we all saw what happened during COVID when our economy ground to a halt because we didn't have the critical semiconductors that we needed to move product in terms of automobiles, industrial equipment. You have some examples here, a 350K mass spec that they couldn't sell because they didn't have a 50-cent chip. But we also have another example of ASML, the famous lithography manufacturer, buying up washing machines to scavenge the chips and put them into their product so they can move product and keep the economy moving. So I would argue that everything I'm going to talk about in terms of expeditionary manufacturing could also apply domestically in a way that will help harden our supply chain against disruptions. So what do I actually mean by expeditionary manufacturing, or at least what does it mean to me? There's a lot of ways to think about it. I have some ideas, and they're almost certainly not the best ideas, and it's definitely not the only way to do it. But in my vision, you have a Marine or a soldier who's forward deployed. They have some mission. They need electronics to carry it out, but they don't have them. So they would need some design or some tool that tells them what chips they need, what passives, what sensors they need to put together to make their item, right? They would need a tool that tells them what commercial items they could go out and acquire to go get those, right? They would also need so they would go out and get them. They would do a teardown of some sort. You have your chips, you put them back together, you reassemble them, you load software, and you deploy, right? So, sounds pretty easy. So why might that actually be hard? I invite you to consider who we're actually asking to pull this off and where, right? We're not talking about teams of double E's from companies like yours with tons of experience. We're talking about 1, maybe 2 20-year-old Marine corporals with, if you're lucky, maybe a couple weeks of fabricator training, right? That's who we're talking about. And they're trying to do it on a ship. They're trying to do it on a beach. They're trying to do it in a tent, right? So this is not where we do traditional microelectronics fabrication. So it's the expeditionary nature of it and where we're asking them and when that really drives the difficulty. So I have some things here. Why is that hard? I invite you to consider, do we have the automated design tools that can support this concept? Do we have a prompt-driven tool where you can say, here's my mission, and it'll tell you what you need to make, where you can go get it? Will it do the design for you? Will it do the routing and the placement and the multi-physics and the thermals and all of that? And then on top of that, if it tells you that you need to go out and get a GE dishwasher, but you can only find a Whirlpool, will it be able to turn around the design all over again quickly so that you can still carry out your mission? If you're able to collect the chips that you need at the chip level and you're trying to do some assembly at the PCB level, where are you going to get the electronic grade materials that you need to put it all together? Can you use the same scrap PCBs that you have lying around? Do we have the tools that can turn around scrap PCBs and turn them into mission-effective assemblies that are good enough for your mission? For that matter, what is good enough for your mission? Does it need to last for weeks? Or is this thing about to blow up in 12 seconds, right? What happens when you press the button and it doesn't turn on? Nothing happens. You need some test and debug tool to tell you, was there a problem with your chip? Did you break the chips when you took them apart? Was there a problem with the fabrication? Can you go back and redo it? All of these are not supported right now. And finally, who's going to write the software for this? Right? If you have millions of different combinations of hardware that you want to put together, and you're effectively MacGyvering together a solution, how does one even approach software for this? So there are many problems here, and probably even multiple DARPA programs worth of problems here. So I invite you, I need your help to help think about this. So for the next problem, or the next idea at least, I'm going to take you even more expeditionary, right? So we're going to go to the moon. All right, so you may have noticed in recent years there's been an increase in commercial activity in terms of lunar activity, lunar landings, new missions that are coming up. For our part, there have been a number of nations that have declared their intent to establish a moon base, right? DARPA, probably actually this week, we published the result of a study that we conducted that describes what we envision a sort of lunar economy to be. If you want access to that, you can just reach out. I can send it over. So I firmly believe that if we as a species are going back to the moon, then we as a nation should be the first to be there. And to me, that all hinges, if we're going to be there, you need the critical infrastructure to make it happen. A lunar economy is built on infrastructure. For me, the appropriate critical infrastructure to think about is power and energy, right? So where are you going to get the power for an economy up there? I would point out that there's a lot of sun on the moon. So there's a lot of access. If you had the photovoltaics, you can generate a lot of power, right? But we're probably not going to ship up millions of tons of solar cells that are depicted in that picture there that NASA thinks. So how are you going to do solar there? Well, you're probably going to have to manufacture at the point of use. I'll point out that lunar regolith is rich in silicon and aluminum, but do we have the tools that we need to purify effectively moon dirt into 6 nines of silicon, right? And probably even more important than that, do those technologies scale so that we can do acres, thousands of acres of solar that we would need? I would argue we don't have those capabilities. While I did say that there's a lot of sun, I'll also point out that lunar night is 14 days long, 14 Earth days long, which means that any power that you generate in the sun needs to be transmitted or stored in the dark region. So we're going to need some sort of energy, some sort of battery, some sort of energy storage, but there's no lithium up there for grid that would support grid scale energy storage. Okay? But there are other elements that could do batteries, like calcium, sodium, magnesium. So I would invite you to think about the types of chemistries that we don't have that we would need to pull it off. And finally, there's something I didn't make it on the slide, but do we have the right power electronics that can do that to do the power handling for grid scale electronics that can survive the hot and cold swings and that can survive the the radiation environment? These need to be in the kilovolts or tens of kilovolts range and operate to do that. There are other opportunities and challenges that faced by the lunar region that didn't fit into power and energy, but cryo temperatures. There are regions of the moon that are permanently cold. So could you do superconducting transmission lines and take advantage of the cryo temperatures? And finally, there's this topic of dust management. This is sort of out there, but lunar dust is coarse, it's abrasive, it's everywhere, it's charged. And so it makes operating and even surviving on the moon very difficult. So we really need some sort of ability to mitigate. And so I invite you, are there crazy ideas out there? Can you sell me a electrostatic force field that can allow us to do some sort of dust-free operations? So I'll leave this slide with another famous quote, and this one comes from my boss. She likes to say that the economic security is national security, and I would argue that goes double for the moon. Okay, so for the last topic, this is way more speculative for me. This is no longer expeditionary manufacturing, but this is one that I think I'm very interested in. So hold on, we're going to get weird. Last year, this group, they demonstrated, they grew a fungus in a petri dish, they attached some electrodes, and they started to read spontaneous spiking signals that occur innately from the biological function of the mycelium, right? They then took that system and they attached it to a soft robot, and it started to move. They ascribed the spiking signals to motion of the robot. Okay, so in effect, what they made was a robot with a fungal brain and nervous system. All right, so this is a really provocative result to me, and I really wonder about how far we can push this. So do we have the right systems, the right microsystems to interface with this? In terms of the ionic signaling? I'll point out that in nature, the mycelium in the ground can span kilometers or tens of kilometers. So can we use it for sensing? Can we use it for communications where you don't have to send RF downrange? So, and then finally, I'll point out here that this example, the spiking and the mapping of the spikes to motion was done by humans, right? So it's not like the fungus was trying to, it's not like it had intent, right? It wasn't trying to move. But what if we can think about this as a growing neural network, and then could it be trained? Could you do reinforcement such that it can interact and react to its environment? All right, can you grow it such that it is trained so that you can propagate it and disseminate it, right? All these problems are fascinating to me, and I hope they're interesting to you, and so I invite you to please come talk to me about it while we're here. Thank you.